Alright, in this video we're going to be talking about the geometry of your panel that you're going to need to calculate for each one of the panels in the mesh after it's been read in from the file. So once everything's been read in from the file, you're going to have a list of panel objects, and for each one of those panel objects we're going to know three basic things. We're going to know the locations of its three vertices. Now we're dealing here purely with triangular panels. That is not required for a panel method, but that's the extent of what we're going to do in this project. Now, based on those three vertices, we need to calculate a few things. We need to know the area of the panel, we need to know its centroid, we need to know the normal vector, the edge tangent vectors, and the edge outward normal vectors. And all of these we calculate right up front because we use them over and over again when we're calculating influence coefficients and other things later on in the panel method. So let's start with area. Now in order to calculate the area of a triangle, I hope you all remember this from your undergraduate days. If you want to know the area of a triangle, you can do that using the cross product. So if I have a vector that defines this first side and another vector that defines this second side, I can find the area of the triangle that those two vectors enclose by taking 1/2 of the magnitude of their cross product. So I'm going to say that A is equal to 1/2 magnitude of. Now for this first vector, remember that to define a vector, it's the end minus the start. So v1 minus v0 crossed with v2 minus v1. That's the area of the panel. Now if we were a quadrilateral panel, I guess you'd have to say a parallelogram panel, then you wouldn't have the 1/2 there. But since we're only dealing with a triangle, we have to include the 1/2 to make sure our result is correct. So that's the first thing, that's the area. Let's talk about real quick, we also need to know the centroid. Well, the centroid is easy. That's just the average of the three vertices. So we can call this, we'll go ahead and call this P sub C. Centroid is equal to 1/3 times the sum over I of VI. And that's all that is. Pretty straightforward. Okay, now let's talk about the normal vector. So we want the outward normal vector to the panel. So if we've got a panel that sits like this, we want to know the unit vector that points up and out of that panel. And we call that n hat, or just a boldface n is what you'll see in the project description. Now if you'll remember that when we take the cross product of two vectors, we get a vector that is perpendicular to both of those vectors. So if we want a normal vector to the surface of this panel, then what we can do is just take the cross product of two vectors that lie in the plane of the panel, and that'll give us a normal vector. So if you remember, we've got v0, v1, v2, and so let's just use the same vectors as we use for our area calculation. And we're going to say that n hat is equal to v1 minus v0, crossed with v2 minus v1. Now we need to make sure that we're doing this in the right order. So if we remember the right hand rule, if we want the normal vector to point out of the panel, then we need to do this vector here crossed with that vector there. The way that I've set up your starter code, actually not the way that I've set up your starter code, the way that the meshes that you have are generated is all of the vertices proceed in the counterclockwise direction around the panel if you're looking at the panel from the outside. So since we know that's the order these vertices are going in, we can exploit that to make sure that n is always pointing outward. Now, this is not guaranteed to be a unit vector, but we want it to be a unit vector, so we're always going to make sure to normalize it. And we just have to divide by its magnitude. And that's it. So that's how we get the normal vector. Let's talk about the edge tangent vectors. Now when I say edge tangent vector, I simply mean a unit vector that is tangent with each edge. So say and I'll introduce our nomenclature, or our standard for identifying edges here. We'll say, and this is arbitrary, but this is the decision we're making, we're going to say that edge 0 starts at vertex 0 and goes to vertex 1. Edge 1 starts at vertex 1 and goes to vertex 2, and so on. So for edge 0, we're going to have a unit tangent vector that sits there. We're going to call that t hat 0. Well, we already know a vector that's tangent to that edge. It's just v1 minus v0. So if we're going to get the unit vector, we'll just take that and we'll divide by its magnitude. That'll give us our tangent vector. We'll compute that for each one of the edges going around this panel. Now, for the last vector that we need to know the edge outward normal. Now, the edge outward normal is a vector that sits in the plane of the panel and is perpendicular to its edge. So if I've got a tangent vector here, t hat 0, then my edge outward normal, and we call that nu hat 0, is perpendicular to t hat 0. So we already know one thing about nu hat 0. We know that nu hat is perpendicular to t hat. Okay. Well, we also know if we want it to be in the plane of the panel, then that means it has to be perpendicular to the normal vector for the panel. So we can also say nu hat is perpendicular to n hat. Sweet. Well, now we need to find a vector that's perpendicular to both t hat and n hat. Well, as we said before, if you take the cross product of two vectors, you get a vector that is perpendicular to both of those vectors. So we can just compute this using a cross product. All we have to do is make sure that we're doing it in the proper order, such that nu hat will point outward. Now, if you remember, if you do your right hand rule, we can say that if we do t0 crossed with n hat, that'll give us nu hat 0. If you're not sure why that is, go ahead and pause the video, pull out your right hand, do the vector, and verify for yourself that t hat 0 crossed with n hat will give you an outward pointing nu hat 0. So again, you're going to calculate one of these for each one of the sides. So for any given panel, we have 3 outward normal vectors, we have 3 tangent vectors, we have 1 normal vector, we have 1 centroid, and we have 1 area. And so all of these are going to be called in your panel initialization, and then you're going to have to store each one of these as part of the panel. Okay, that's it for these geometric vectors that we're dealing with. We're now going to talk about a coordinate transformation. So when you calculate the velocity jump across your panels, you're going to do so in what we call the local panel coordinate system. So let's talk about what that is. If I've got a panel, and that panel is defined in whatever coordinate system the mesh came in. So say it's some Cartesian coordinate system x, y, z, and that's just, the panel's just floating off in space. It really has arbitrary orientation, arbitrary position, and so, it's defined however it wants to relative to that global coordinate system. But we're also going to define a local coordinate system. And this local coordinate system is defined such that the x and y directions are in the plane of the panel, and then the z direction is normal to the plane of the panel. So our z component is just the height above the panel, and x and y are displacements within the plane of the panel. And we're going to call this the primed coordinate system, so z prime, y prime, x prime. Now we want to be able to easily switch back and forth between these two coordinate systems. Oh, and we're also, before I move on, let's point out that the origin of this coordinate system is at the centroid of the panel, so P sub c, that we calculated just before. So, how do we make a transformation between these two? Well, let's go to a real simple example first. If I've got just a simple two-dimensional Cartesian plane here, this is x, this is y, and this is going back to your linear algebra days. If this has all been a little unfamiliar to you, you might want to go back to your linear algebra textbook and review coordinate systems, coordinate transformations, linear spaces, that kind of thing. So in my Cartesian coordinate system, my coordinate system is defined by two vectors. Oh, come on. We'll just keep it blank. Okay. Our coordinate system is defined by two unit vectors, e hat x and e hat y. And if we write these in this coordinate system that we've already defined, then we'll have that e hat x is equal to 1, 0. Okay? And e hat y is equal to 0, 1. So if I wanted to find the x and y components of some vector, say a here, then all I would need to do is dot a with each one of my unit vectors, and that'll give me the components. So ax is going to be equal to a dotted with e hat x. And ay is going to be equal to a dotted with e hat y. Now, in order to make this computation work, all we have to do is make sure that these vectors are expressed in the same coordinate system. And then these ones here will be in terms of this Cartesian coordinate system I've defined. Well, I can define a different coordinate system. I don't have to use this coordinate system that I've got here. So let's scroll down. Let's draw up our old coordinate system. We've got x, we've got y. But let's say I want to define a primed coordinate system. I'm going to say that this is my new x direction, ex prime, and we'll say this is my new y direction, e hat y prime. And so if we wanted to write these out in the original coordinate system, e hat x prime, it'd be something like 1 over the square root of 2, 1, 1. And e hat y would be something similar, just different signs. And then we could say, okay, if I want to express, again, I've got some arbitrary vector a, and say I wanted to just express this vector in this new primed coordinate system, well then a x prime is simply equal to a expressed in the global system dotted with e hat x prime also expressed in the global system. And then a y prime is equal to a dotted with e hat y prime, again all expressed in the global coordinate system. So again, we take the dot product of two vectors that are expressed in the global coordinate system, and that gives us the coordinates in our new coordinate system. Pretty slick. So how do we do this for our panel? Well, first we need to pick our coordinate directions. Again, like I said, if this is our panel, then we're going to define our coordinate system as having x and y sitting in the plane of the panel, and then z is going to come out and be normal to the panel. So in order to define this coordinate system, we need to figure out, okay, what are e hat x prime? Oh, I forgot, these are primed. What is e hat x prime? what is e hat y prime, and what is e hat z prime? Well, these are just unit vectors that describe these directions. Let's start with the easy one. Let's start with e hat z prime. Well, like we said, we want the z direction to be perpendicular to the plane of the panel. We want it to be normal. Well, we already have a normal vector. So let's just say e hat z prime is equal to n hat. Well, that was easy. Okay, we've got our first coordinate direction. Okay, well now, what about e hat x prime and e hat y prime? So for incompressible flows, the direction of these are arbitrary as long as they're in the plane of the panel. If you get into the world of compressible flows where you're solving the Pareto-Glauert equation instead of the Laplace equation, the direction of x prime and y prime actually matter. But we're not going to worry about that right now. So we can pick any arbitrary vectors for x and y as long as they're in the plane of the panel and complete a right-handed coordinate system. So I'm going to start with e hat x prime, and I'm going to say, well, a vector that I know is in the plane of the panel is just the tangent vector of the first edge. So I'm just going to pick e hat x prime. Oh, I drew that prime in the wrong spot. E hat x prime is just e hat naught. That was easy. Okay, that one's taken care of. And then all we need to do is pick e hat y prime to take care of the rest of the right-handed coordinate system, which, if you'll remember the order of these unit vectors, then that's going to be n hat crossed with t hat naught. Now again, the selection of t hat naught is completely arbitrary. You could have picked any vector in the plane of the panel. You could have picked nu hat naught, you could have picked t hat 2, you could have picked some average of any of those, you know, it's really arbitrary. But as long as you pick e hat y prime, so that it's perpendicular to the other two, the x direction can be whatever you want. So if you want to pick a different one in your panel method, that's just fine. I won't be offended. Just as long as you're consistent. So let's move on. Now we've got our unit directions. So going back to what we did before, if I've got some arbitrary vector A, and I want to express it in the prime coordinate system. So what is A in the prime coordinate system? Well, all I got to do is I'm going to have ax prime is the dot product of e at x prime with a. Both of those are expressed in the global coordinate system. And we'll do that for the rest of the components. Now we can write this as a vector. So we end up with this vector expressed here in the local coordinate system, and it's a vector of these dot products. Now rather than do that, we can also say this is equal to a matrix vector product, where we have a matrix where the rows are now the direction vectors for our local coordinate system. So e hat x prime, e hat y prime, e hat z prime. And then all we're doing is multiplying a by that vector, and that will give us a in the new coordinate system. Now, it's really important that you understand that these two calculations are equivalent. If you're a little shaky on it, please pause the video, go grab your linear algebra textbook, and verify for yourself that a matrix vector product is the same as a distributed dot product of that vector with the rows of A. And make sure you're very clear on that. Okay, now one last thing. If A is a position vector, and we're concerned about its actual location in space, imagine we've got our imagine we've got our global coordinate system and its origin is down here, x, y, z, and we've got some arbitrary vector a. Well, what if we've got our panel over here and it's got its local coordinate system? And remember we said that the origin of the local coordinate system is at the centroid of the panel. So A in the local coordinate system is going to look like that. This is A prime, and we can write its components in the local coordinate system. So we need to do that shift of origin. So in order to do that, if we've got some arbitrary position vector A, and we want it in the primed coordinate system, we're going to do, oh, I should go back here real quick. This matrix here, we are going to call A, G to L, signifying this is the A matrix that will transform from global coordinates to local coordinates. So if we call that A, G to L, then this equation here is simply A prime is equal to A, G to L times A in the global system minus our centroid, P, C. So this part of the equation takes care of that shifting of origins, and this part of the equation takes care of the fact that we've now rotated the coordinate system. Now there are some vectors where the location really doesn't matter. So if you're dealing with position vectors, then yes, you need to do this shift. You need to do the shift of origin. But if you're dealing with something like a velocity vector or an acceleration vector, those don't care about the origin. They're just applied wherever they're applied, and so you only need to perform a rotation for transforming a velocity vector from global to local coordinates, or vice versa. Now that's the really cool thing about AG to L, is that since we've made it up of, since its rows are orthogonal unit vectors, AG to L is what's called an orthogonal matrix. And for an orthogonal matrix, we have that AG to L inverse is equal to A G to L transpose. So that's a really nice thing about setting up this coordinate system the way we've done it, is that in order to go from global to local coordinates, we just use AG to L. In order to go back, you don't have to invert the matrix. All you need is to take its transpose, which makes life really, really easy. So again, if let's do this in terms of like a velocity vector now. If I've got some velocity vector that I want in the global coordinates, then I could say that this is A, G to L transpose times that velocity vector expressed in the local coordinate system. Again, remember, for velocity vectors, you don't have to do a shift of origin. They're just applied wherever they're applied. That's it for this video. I hope you enjoy getting these equations all implemented in your code, and we'll see you next time.